Look inside a modern electric vehicle, a medical scanner, a semiconductor factory, a satellite instrument, or an artificial hip, and you will find a material that looks almost too ordinary to matter. It is usually white. It does not shine like titanium or glow like silicon. It has no moving parts and carries no current. Yet it survives voltages that would punch through plastic, temperatures that would soften metals, chemicals that would corrode steel, and friction that would destroy most engineered surfaces. The material is alumina ceramic, aluminum oxide formed into an exceptionally dense solid. Today it appears in electronic packages, vacuum feed-throughs, high-voltage equipment, armor, surgical implants, industrial valves, sensor housings, and the machinery used to manufacture computer chips. But one of the decisive steps in turning alumina from a chemical powder into a practical high-technology material came from a component small enough to fit in a mechanic's hand: the spark plug insulator. In February of 1942, as American factories were being reorganized for war, the United States Patent Office granted General Motors a patent for a dense, non-porous ceramic body containing roughly 85 to 99% alumina. Its named inventors, Albra Fessler and Karl Schwarzwalder, described a material built mainly from tightly sintered crystals of corundum, the crystalline form of aluminum oxide, with only a small amount of glass between them. They emphasized high-temperature electrical resistance, thermal shock resistance, mechanical strength, and improved heat conduction. Those were not abstract laboratory properties. They were exactly what a spark plug needed inside a hard-working engine. The date in the patent was 1942, but the work had begun years earlier, and alumina itself was not an American invention. European ceramic researchers had already explored high alumina and sintered corundum materials. What the American program helped solve was the industrial problem: how to take a powder with almost no natural plasticity, compress it into a complicated insulator shape, fire it until its microscopic grains locked together, and do it repeatedly enough for engines, radios, aircraft, and eventually electronics. That problem created a new kind of ceramic. It did not belong to the ancient world of pottery, dinnerware, or brick. It belonged to the emerging world of precision materials. The white shell around a spark plug electrode became one of the quiet starting points of the advanced ceramics industry. A spark plug appears simple because nearly all of its difficult engineering is hidden. The threaded steel shell screws into the cylinder head. A central conductor carries a high-voltage pulse from the ignition system. At the firing end, that pulse must cross a small air gap to the grounded electrode. The electrical arc ignites the compressed fuel and air mixture. But electricity always searches for the easiest path. The purpose of the ceramic insulator is to make every path difficult except the one across the intended spark gap. It must stop tens of thousands of volts from leaking through the plug body or sliding across its surface. At the same time, it must hold the center electrode accurately, seal combustion pressure, transfer heat away from the firing tip, and survive violent changes in temperature. Every time the engine fires, the lower end of the insulator is exposed to hot combustion gases. A moment later, it is cooled by incoming mixture and by heat flowing into the cylinder head. It is shaken by engine vibration, struck by pressure waves, contaminated by oil, carbon, and metallic fuel residues, and clamped inside a steel shell that expands differently when heated. A microscopic pore can become an electrical pathway. A tiny crack can grow under thermal cycling. A weak, glassy region can soften or conduct current at the worst possible moment. Early spark plugs used materials inherited from traditional ceramics. Their insulators were commonly made from porcelain bodies containing clay, feldspar, quartz, and other mineral ingredients. These materials could be mixed with water, shaped while plastic, dried, and fired in a kiln. That made manufacturing familiar and inexpensive. But the same ingredients that made porcelain easy to form also created weaknesses. When traditional porcelain is fired, part of it becomes crystalline and part becomes glass. The glass fills spaces and helps make the body impervious, but it also controls many of the final properties. At ordinary temperatures, the material may be a good insulator. At the high temperatures near a combustion chamber, however, alkali impurities and glassy phases can allow greater electrical leakage. The body may also conduct heat poorly, allowing the firing tip to overheat, or it may crack when temperature changes too quickly. By the First World War, aircraft engines had already exposed these limitations. In 1920, the National Advisory Committee for Aeronautics published detailed experiments on spark plug insulators, comparing porcelain, feldspar, quartz, cements, and other compositions. The goal was not cosmetic improvement. An aircraft engine could not simply pull over to the side of the road when a plug failed. Ignition reliability was a flight safety problem. Engine technology continued to raise the pressure. Compression ratios increased. Cylinder temperatures rose. Ignition systems delivered higher voltages. Aviation fuel gained tetraethyl lead because it allowed engines to resist knock and produce more power. But leaded fuel created deposits that could attack or electrically foul insulating surfaces. By the early 1940s, American engineers were designing aircraft spark plug ceramics specifically to resist lead-containing combustion products in high-compression engines. The old porcelain approach was reaching a boundary. Spark plug makers did not merely need a slightly better glaze or a slightly different clay. They needed a body whose properties came from strong crystals rather than from a continuous network of glass. Alumina offered that possibility. Chemically, alumina is aluminum oxide, written as Al2O3. In nature, its crystalline form is corundum. Trace elements can turn corundum into ruby or sapphire, but the industrial material begins as a white powder. It is hard, chemically stable, electrically insulating, and capable of remaining strong at temperatures that defeat many ordinary materials. The difficulty is that alumina powder does not behave like clay. Clay becomes plastic with water because its particles interact in a way that lets the mass be molded. Fine alumina behaves more like dry sand. It will not willingly hold the long, narrow, hollow shape required for a spark plug insulator. This manufacturing obstacle was as important as the chemistry. General Motors researchers approached the problem by separating shaping from the traditional idea of plastic clay. The 1942 patent described mixtures dominated by alumina with controlled amounts of silica-bearing material and, when needed, small additions that helped sintering. Instead of depending on large quantities of clay, the powder could be mixed with a temporary organic binder, including thermosetting resin and a lubricant. The mixture was first pressed into a preliminary form. Then it was subjected to enormous pressure in a mold on the order of tens of thousands of pounds per square inch. The pressure packed the particles closely enough to create a fragile green body. It looked solid, but it had not yet become ceramic. The binder held it together only long enough for the firing operation. Inside the kiln, the organic material burned away. As the temperature climbed, the alumina particles began to bond where they touched. Atoms moved across grain boundaries. Pores shrank. Separate powder grains became a dense polycrystalline structure. This is sintering. The body does not have to melt completely. In fact, complete melting would destroy the carefully formed shape. Instead, the ceramic is fired below its full fusion temperature until its grains weld together. The part shrinks, sometimes dramatically, and every dimension must be designed with that shrinkage in mind. The General Motors patent described finished bodies made primarily of corundum, and in some formulations, mullite, with only a small proportion of glass occupying the remaining spaces. This reversed the structure of conventional porcelain. In older bodies, a large glass phase often controlled the properties while crystals floated within it. In the new high alumina body, the crystalline skeleton controlled the performance and the glass became a minor participant. That difference changed everything. More alumina increased density and mechanical strength. It improved thermal conductivity, allowing heat to move from the firing tip into the plug shell and cylinder head. It increased resistance to thermal shock because temperature gradients became less extreme. It improved electrical resistance at elevated temperature. And because the body could be sintered until almost no open porosity remained, electricity and combustion gases had fewer microscopic paths to exploit. The patent warned that even porosity measured in hundredths of a percent could be objectionable in a spark plug insulator. That statement reveals the new standard of ceramic engineering. Pottery can tolerate pores, A flower pot is designed to breathe. A dinner plate may contain small imperfections and still function. A high-voltage insulator operating in a hot engine cannot. The ceramic had to become not merely hard but controlled. The timing of the patent could hardly have been more significant. 10 weeks before it was granted, the attack on Pearl Harbor had pulled the United States into the war. American industry now had to build engines for fighters, bombers, tanks, trucks, landing craft, generators, motorcycles, and countless support machines. Each gasoline engine depended on ignition. Multi-cylinder aircraft engines required many plugs, often 2 per cylinder for reliability and combustion efficiency. Each plug had to survive long operation under heavy load. In March 1942, the Society of Automotive Engineers issued an aircraft engine spark plug standard covering 18-millimeter plugs. That same month, an American patent application was filed for an aircraft spark plug ceramic specifically resistant to corrosion from lead-containing fuel residues. The wartime problem was broader than one patent or one company. It involved General Motors and AC Sparkplug, Champion, specialized ceramic suppliers, aircraft engine builders, military laboratories, standards organizations, and fuel researchers. High-octane leaded aviation fuel made engines more powerful, but it also made the plug environment more hostile. Lead compounds could form conductive or corrosive deposits on the insulator nose. If the tip operated too cool, carbon and fuel residues accumulated and created a leakage path. If it operated too hot, it could ignite the mixture before the spark arrived, causing pre-ignition and engine damage. The ceramic's ability to conduct heat was therefore not a simple matter of more is better. Engineers had to control the heat path so that the plug reached a self-cleaning temperature without becoming a hot spot. This is the origin of the spark plug's heat range. A hot plug keeps more heat at the firing end, usually through a longer insulating path. A cold plug transfers heat away more quickly. The chemistry of the ceramic, the length and thickness of the insulator nose, the metal shell, and the contact surfaces all work together. Alumina gave designers a stronger and more thermally capable material, but geometry still determined how the plug behaved in a particular engine. Manufacturing consistency became as important as laboratory performance. A ceramic that worked perfectly in a test sample was useless if one production lot shrank more than another, if density changed from top to bottom, or if hidden cracks appeared during pressing. Spark plug insulators are long relative to their diameter and contain a central bore. Powder must pack uniformly around that bore. Uneven density becomes uneven shrinkage, and uneven shrinkage bends or cracks the part. American manufacturers developed several ways to solve this. One was isostatic pressing, in which pressure is applied around a flexible mold, so the powder is compressed more uniformly from multiple directions. Champion Sparkplug was experimenting with isostatic forming of alumina insulators in the 1930s. In 1940, when Champion chose to concentrate on spark plugs, Coors Porcelain acquired parts of Champion's chemical and scientific porcelain business, along with industrial processes including isostatic forming and spray drying. During the war, Coors shifted away from consumer dinnerware and concentrated on technical porcelain products. Spray drying helped turn fine ceramic slurry into controlled, free-flowing granules. Each granule contained powder and binder in a form that filled dyes more uniformly. Isostatic pressing reduced density gradients. Precision machining shaped the unfired blank while it was still soft enough to cut. Carefully controlled firing transformed it into dense ceramic. Diamond grinding finished surfaces after sintering, because hardened alumina quickly wears ordinary cutting tools. The process was not simply a ceramic version of metalworking. Metal can often be machined to final dimensions after it is fully dense. Alumina becomes so hard after firing that extensive machining is slow and expensive. Manufacturers therefore had to produce near final geometry before sintering, predict shrinkage, prevent distortion, and reserve only critical surfaces for diamond finishing. The central hole created another problem. The electrode had to be sealed into the insulator without cracking it or allowing combustion gases to leak upward. A Champion patent filed in February 1942 described pre-firing the ceramic until most shrinkage had occurred inserting the electrode and then using a rapid final firing to shrink the remaining bore into tight contact. Other designs used glass seals, conductive glass mixtures, cements, and carefully matched metals. Every interface mattered because ceramic and metal expand at different rates. Heat a badly designed assembly, and the metal may pull away, crush the ceramic, or place it under tension. Ceramics are extremely strong in compression, but relatively weak when a crack is opened in tension. The spark plug became a compact lesson in joining dissimilar materials, controlling thermal expansion, sealing high pressure, and carrying high voltage through a hostile environment. Wartime production accelerated these lessons. The military did not require a few record-breaking plugs. It required millions of acceptable plugs whose behavior could be predicted. That pushed manufacturers toward statistical inspection, standardized tests, controlled powder chemistry, calibrated kilns, and disciplined quality systems. The advanced ceramic industry grew not only from discovering good compositions, but from learning how to make those compositions repeatably. The result was a material that could tolerate the three enemies of ignition: heat, electricity, and contamination. Its electrical behavior came from strong ionic bonds and a microstructure with very few conductive impurities or pores. The ceramic forced the voltage to remain in the center conductor until the electric field across the spark gap became strong enough to ionize the gas. Ribs on the outside of the insulator increased the distance that leakage current would have to travel along a dirty surface. Glaze made the exterior smoother and less likely to collect moisture and grime. Its thermal behavior came from the alumina crystal network. Alumina conducts heat better than many traditional porcelains, while still remaining an electrical insulator. That unusual combination is valuable far beyond spark plugs. Metals conduct heat well, but they also conduct electricity. Plastics insulate electrically, but often soften, burn, or conduct heat poorly. Alumina occupies a useful middle ground, electrically resistant, thermally capable, mechanically stiff, and stable at high temperature. Its mechanical behavior came from hardness and compressive strength, but also from the elimination of defects. A perfectly bonded crystal lattice is extraordinarily strong. Real ceramics fail at pores, inclusions, oversized grains, machining scratches, or surface cracks. Advanced ceramic manufacturing is therefore largely the science of controlling imperfections. Powder purity, particle size, pressing uniformity, firing atmosphere, peak temperature, grain growth, surface finish, and inspection all influence whether the final part survives. That same logic explains why alumina spread after the war. The first expansion was electronics. Alumina has been used in electronic packaging since the 1940s because it can support conductors while insulating them from one another, withstand heat from components, remain dimensionally stable, and form hermetic bonds with metal. Instead of carrying one electrode through a spark plug, ceramic packages could carry many electrical connections into sealed devices. Manufacturers learned to metallize alumina by applying specially formulated metal pastes and firing them so they bonded to the ceramic. Metal frames, pins, and lids could then be brazed into place. The resulting package protected sensitive electronics from moisture, contamination, vacuum loss, and mechanical damage. As electronic circuits became smaller, alumina became a substrate on which conductive tracks, resistors, and components could be built. High-temperature co-fired ceramic allowed layers of alumina and refractory metal conductors to be stacked and fired together. A material developed to keep one ignition pulse from escaping could now organize thousands or millions of electrical events inside communications, control, and sensing systems. Modern alumina packages are used for quartz crystal devices, image sensors, light emitters and detectors, optical communications, radio frequency components, and high-reliability electronics. Their coefficient of thermal expansion is closer to silicon than many organic packaging materials, reducing stress as chips heat and cool. Their stiffness limits warping. Their electrical insulation keeps densely packed signals separated. Their thermal conductivity helps move heat away from active devices. The second expansion was into vacuum and high voltage. The spark plug had already taught engineers how to join ceramic to metal while preserving electrical isolation and gas tightness. The same idea became the ceramic feed-through, a conductor passing through an alumina body that is brazed into a metal wall. Feed-throughs carry power and signals into vacuum chambers, X-ray tubes, particle accelerators, satellite instruments, semiconductor processing machines, and scientific equipment. Inside these systems, the ceramic may face conditions more extreme than any piston engine. One side can be at atmospheric pressure, while the other is under ultra-high vacuum. The part may be heated, cooled to cryogenic temperature, exposed to radiation, or surrounded by aggressive plasma. Yet the basic demand is familiar: hold the conductor precisely, stop electricity from taking the wrong path, survive temperature change, and maintain a seal. New alumina grades now insulate equipment operating from several thousand volts to nearly 1,000,000 volts. They appear in mass spectrometers, electron microscopes, medical CT and MRI systems, X-ray equipment, and accelerator hardware. The shape may be a flat substrate, a tube, a ring, a chamber, or a multi-pin connector. But the material logic is the same logic that made the spark plug insulator possible. The third expansion was wear protection. Alumina is extremely hard. Once manufacturers learned to form dense, controlled bodies economically, it became useful wherever metal surfaces were being ground away by abrasive particles, sliding contact, or corrosive fluids. Alumina liners protected chutes and pipes. Ceramic seals resisted wear in pumps. Valve components survived chemical processing. Textile guides, cutting tool inserts, grinding media, and industrial nozzles used the same combination of hardness and chemical stability. In these applications, brittleness remained the limitation. Alumina does not yield like steel. It can carry enormous compressive loads, but a sharp impact or tensile crack can break it suddenly. Engineers learned to design around that weakness by keeping ceramic parts in compression, rounding corners, controlling surface finish, backing them with tougher materials, and improving grain structure. That strategy led to ceramic armor. In the 1960s, alumina tiles were combined with fiberglass and polymer backing to create protection lighter than comparable steel against certain threats. The hard ceramic face damaged and eroded the projectile. The backing caught fragments and distributed the remaining load. Alumina became widely used because it offered strong ballistic performance at relatively low cost. Lighter ceramics such as boron carbide and silicon carbide later became preferable for many personal armor systems, while alumina remained important where cost and weight requirements allowed it, especially in vehicle and structural protection. The connection to the spark plug is not that armor uses the exact same recipe. It does not. Armor grades, electronic grades, medical grades, and ignition grades are engineered differently. Some contain more than 99% alumina. Others include glass-forming additives, magnesium oxide to control grain growth, zirconia to improve toughness, or specialized dopants that change electrical behavior. The connection is deeper. All belong to the industrial family of dense, sintered alumina ceramics whose manufacturing foundations were established through early electrical applications. The fourth expansion entered the human body. In 1971, alumina ceramic bearings were introduced into total hip replacement. Their hardness, chemical inertness, smooth finish, and low wear made them attractive alternatives to surfaces that released metal ions or polymer debris. The demands were severe. A hip joint cycles millions of times under body weight. The surfaces must remain smooth, resist scratching, avoid corrosion, and generate as little wear debris as possible. Early medical ceramics were not perfect. Large grains, residual pores, poor design, or surface defects could cause fracture. Over decades, manufacturers increased purity, reduced grain size, used hot isostatic pressing, improved proof testing, and polished components to extraordinary accuracy. Modern implant ceramics include high-purity alumina and zirconia-toughened alumina composites, which combine alumina's wear resistance with improved fracture strength. Alumina also appears in the electrical feed-throughs of implantable medical devices. A pacemaker, neurostimulator, or defibrillator must transmit signals through a sealed enclosure while keeping body fluids away from its electronics. The challenge resembles a miniature spark plug turned inside out. Conductors must pass through an insulating ceramic, the metal-to-ceramic joint must remain hermetic, and the assembly must survive for years in a chemically active environment. The fifth expansion reached the semiconductor factory itself. Chip manufacturing uses plasmas, corrosive gases, vacuum, heat, and extremely clean surfaces. Alumina components serve as chamber domes, windows, lids, liners, nozzles, sleeves, plates, and insulators. High-purity grades resist erosion and reduce contamination. Polishing plates use alumina's stiffness and wear resistance. Ceramic substrates support power modules used in electric vehicles, telecommunications, renewable energy systems, and industrial controls. This creates a striking loop in technological history. Early alumina ceramics were developed because electrical systems needed insulation that could survive heat. Modern electronic systems require alumina not only inside their packages, but inside the machines that manufacture the electronics. The material protects the chip, helps build the chip, controls power around the chip, and carries signals into the vacuum equipment used to inspect the chip. Even the original application has not stood still. Modern gasoline engines use higher compression, leaner mixtures, direct injection, and smaller cylinder head packaging. Ignition systems may demand higher voltage from a smaller plug. Conventional spark plug insulators are commonly made from roughly 90 to 95% alumina, with carefully controlled glass and oxide additions. Newer high-performance designs move closer to pure alumina and use dopants to reduce high-temperature leakage. Compaction pressures, powder preparation, firing cycles, and quality control have advanced far beyond the methods of the 1930s. Yet, a modern study of aircraft or turbine engine igniter ceramics still returns to cold isostatic pressing, powder density, pores, cracks, hardness, and alumina purity. The equipment is computerized, and the analysis may use finite element simulation. But the core manufacturing question remains recognizable. How do you compress a non-plastic powder into a complicated hollow shape and sinter it without leaving a defect that high voltage, pressure, vibration, or heat can find? That question is now being attacked with additive manufacturing. Ceramic three-dimensional printing can build internal channels and complex shapes that are difficult to press or machine. NIST identifies ceramic additive manufacturing as important for body armor, electronics, energy, medical implants, high-temperature systems, and structural components. But printed ceramics still face the old enemies: incomplete density, weak layer interfaces, shrinkage, defects, cost, and certification. The future of alumina depends on solving the same problem that defined its past: controlling structure at every scale. One reason alumina continues to survive newer materials is economic. It is not the lightest armor ceramic, the toughest structural ceramic, or the best conductor of heat. Aluminum nitride, silicon carbide, boron carbide, zirconia, and silicon nitride can outperform it in particular categories, but alumina offers a balance of performance, availability, manufacturing maturity, and cost. Bauxite is processed, and decades of experience have produced powders, binders, presses, kilns, diamond tools, and inspection methods built around it. Engineers can select grades from roughly 80% alumina to purities above 99%. Trading price, strength, dielectric behavior, corrosion resistance, and machinability. High technology does not always choose the most extreme material. Often it chooses the most dependable compromise. The material itself is also evolving. Alumina can be combined with zirconia to create tougher composites. It can be made porous for filters or bone growth structures, or nearly transparent for optical and protective applications. Grain orientation can be controlled to tune properties. Thin alumina layers can be co-fired with metals into three-dimensional circuits. High-purity formulations can survive stronger plasmas and higher electric fields. Engineers now design not just the chemical composition, but the grain size, grain boundaries, residual stress, surface texture, and distribution of secondary phases. This is why the phrase ceramic can be misleading. It suggests something old, brittle, and simple. But advanced ceramics are engineered from powders, with the same seriousness applied to superalloys or semiconductor wafers. Their performance depends on chemistry measured in fractions of a percent, particles measured in micrometers or nanometers, furnace cycles controlled across hours, and inspection capable of finding flaws invisible to the eye. The 1942 General Motors patent did not create every modern alumina product. It did not invent corundum, sintering, or the idea of ceramic insulation. Its work had begun in the mid-1930s, and parallel progress was taking place in Europe and at other American companies. History rarely gives one material a single inventor or birthday, but the patent captured a decisive transition. It described a spark plug insulator no longer dominated by clay and glass, but by a dense skeleton of engineered crystals. It addressed powder preparation, high-pressure forming, firing, porosity, high-temperature electrical behavior, thermal conductivity, heat shock, and mechanical strength as parts of one integrated system. Those are the foundations of technical ceramics. The spark plug was the perfect forcing function. It was cheap enough to require mass production, complicated enough to demand precision, and exposed to conditions harsh enough to punish every hidden defect. A material that could survive there had value almost everywhere. That is why the white ceramic in a spark plug should not be dismissed as a piece of porcelain. It represents the moment ceramic engineering moved beyond copying natural stone and began constructing controlled microstructures for specific functions. Inside a wartime engine, the alumina body had one job: keep the ignition pulse trapped until it reached the gap. In a modern semiconductor package, it separates microscopic circuits while carrying away heat. In a vacuum feed-through, it holds a seal around a conductor. In an artificial hip, it provides an exceptionally smooth, wear-resistant bearing. In armor, it attacks a projectile with hardness. In a chip factory, it stands between corrosive plasma and the machines that create the digital world. Different grades, different shapes, different additives, different standards, but the same underlying material family and the same central bargain. Accept brittleness in exchange for heat resistance, electrical insulation, hardness, chemical stability, and dimensional control that metals and polymers cannot provide together. The ceramic developed for spark plugs did not remain inside the engine. It became a platform. And the most remarkable part of its story is not that a 1942 patent still matters. It is that modern technology continues to ask the same question those engineers faced. What material can stand next to heat, voltage, pressure, friction, chemicals, and time, and refuse to change? For more than 8 decades, one of the best answers has been alumina.